So hi. Today I'm very excited that we have Shi Qiu here from Nikhef and Utrecht University. Shi completed his bachelor's degree from Monash University in Australia, and his master's degree from Lund University in Sweden, where he was part of the Atlas experiment and worked on exotic ink searches. Yeah. Currently, he is in his final stages of his PhD with the Atlas collaboration, where he works on searches for the chiral magnetic effect. In addition to data analysis, he redesigned the Atlas CBC calibrations and also did a hardware project for his service work. Today he's going to talk about search for chiral magnetic effect in heavy ion physics with Atlas.
Thank you for the introduction. So quite honored to come here to present. So as I said, I will present basically the stuff I did during my PhD. Does it work? Actually, it doesn't work.
Sometimes if you click click your screen, and now try it. Does that work? No?
Does it work on the...
So now try it.
Well, it doesn't like my laptop.
I'm sorry.
That's one.
You can do the...
Yes.
Okay.
Yeah, so as I said, this is outline roughly. So basically, I first introduce what is the chiral effect. Now I will talk about this main analysis which I did with using this thing called the spectator-participant method. And also I will talk about another side project which I work with phenomenology models, also studying CME. And also very briefly, actually just one slide, I talk about this radiation hardness test. And I also share a bit of my future interest. So let me start with the introduction. So the theory of this CME is quite interesting and also actually quite complicated. So, but I give a very brief structure of how it happens. If you want to know more, you can talk to me. Basically, you start with this non-abelian theory, which is the reminder is SU3 to the D, also SU2 electron weak. And from this theory, you can get a vacuum configuration. It has a different winding number. And this different winding number means each ground state differ with each other. And you cannot, they call it topological different, which means you cannot make a smooth transition from one ground state to another ground state without leaving this ground state. This is what they mean by topology. And yes, of course, this. And okay, this is the picture. So in a quite pictorial way, we have this configuration looks like this periodic shape. And this is a winding number. You can make a transition. You have to leave this ground state, but you can do it with either tunneling with the instanton, also with crossover with the sphalerons. So sphalerons is like you have excitation to the top, then it decay to another state. It's another way of making this transition. And yes, of course, this instant happens when this energy just below this height of potential, and the tunneling rate is suppressed by the height of potential. And the sphalerons is energy is above this potential. And this is a classical expression. Later I will show a bit more like series calculation, but this is as you can see that this is called thermal, which means if the temperature is high enough, you have a lot of thermal energy in your system, you can actually excite your sphalerons to cross this potential. And the change in the winding number is associated with the quantum anomaly. And this is quantum anomaly means non-conservation of some quantum number. And here, as I say, this is non-abelian Yang-Mills theory. You can have a QCD and electron weak. And there are two types of non-constant quantum. For QCD, it's related to chirality. And for electron weak, it's related to baryon electron number. The higher potential, so let me first talk about this chirality. So this is just very brief of what is the connection. Basically, you see the the transition between the different vacuum configuration. Which you can see, you have this bracket. You have this early cycle 1 dynamic transition by Q. You calculate this transition amplitude. You can relate this to, if you do the calculation, you will see its form is same as this thing called axial anomaly. And this axial anomaly is something, I don't know if I've heard, but it takes a bit more time to explain. This is some quantum anomaly in the triangular diagram, which is related to this chirality imbalance. So basically, what I want to say is that with the transition in the ground state, you can connect to this chirality imbalance. Okay, so well, for this, the height of potential is still hard to estimate for TCD because it's non-perturbative. For the electric weak, it's being estimated to be 10 dB, so it's very high potential. And you need there's some paper which did the estimation. You need a quite high energy population to reach a sizable what's it called? This is the probability. And for the heavy ion, this is roughly well, people have some speculation. This is roughly like lambda QCD. This is potentially accessible in the heavy ion equation because it has this very high temperature. Okay, so also in the heavy ion equation, we have this spectator, which is the particle which do not participate in the collision. They create very high magnetic field. And also, I put some other text just to explain for if anyone like who's new to heavy ion, like we have also have this impact parameter, which describes the distance between the center of the chemical. They're related to centrality from 0 to 100%. And it also means from central to peripheral. And also you see this plot, you also see the arrow that pointing upward. This is also this is showing the direction or magnitude of the pressure gradient. And this is also called the anisotropy curve, which I will also talk a bit more later. You can see that there's some simulation of this magnetic field, right? Basically, this is the time. It gets extremely fast. Basically, you see the formation of QGP is sometimes thought of to be around the 1 Fermi, but it actually decays super fast. But there is also very strong magnetic field. It's like 10 to the power 15 Tesla. Okay, so the current magnetic field is really just you have the transition in this non-trivial QCD vacuum structure. This leads to chirality. This leads to this chirality imbalance. And with this, under this magnetic field, strong magnetic field, because the magnetic field usually align the spins, and you have different chiral. Actually, we put it's called chirality, but for us, we're really talking about helicity. Right? So you have this momentum actually has the point with this handiness, and then you have this CME, which is the charge separation. And the heavy ion collision really is a perfect environment to look for this phenomenon. And this is just putting everything together. You have this spectator creating magnetic field, and you have charge separation across the reaction plane. Basically, you have like a dipole. Okay, and I also want to say a bit of like unknowns in this field. So the first is this magnetic field. This is we still don't understand like how long it lasts. It's lifetime, because also we have not measured. Like this in this AVFD model, which I also talk about, but actually in model you can have different parameterization of description of this magnetic field. Also, its conductivity is, of the system is not well known. There are some lattice simulation which says it can drop with the temperature. Of course, the conductivity is related to its the lifetime of the D field. But these are not known. Also, the transition rate of the spiral, before I show this classical rate, but a bit more serious lattice calculations suggest that this rate decreases as the plasma evolves. So this rate is actually constantly changing. And we actually not exactly sure this sphalerons transition when it happens. Also, this part it's mainly this background and the hydrogenation. So this first part, what I mean is this kinetic dynamic, which is the background. So the main background, which also will come back to it, is this electric charge conservation in the local phase space. And this is coupled to this anisotropic expansion. And this is, we never have a Monte Carlo model which simulates this from the first principle. We have some phenomenology model. Also, the hydrogenation is also like, it's not super well understood in the heavy ion collision. Also, like here, we have this chirality. You can imagine you have this quark, which has different chirality formed at the beginning, but how they really combine to hadrons. Yeah. So, okay, so now I talk about this main analysis, which I use this spectator-participant method. The first.
If you go back, so I thought the chirality, when it's conserved over the medium, right? When this imbalance is only.
It's local.
Local.
It's local. Yeah, exactly. It's local. So I talk about this. Okay, now I talk about this experimental observer, which is proposed which is sensitive to this kind of charge separation across the event plane. And its construction is essentially it's a three-particle correlator. You have this. It's called gamma correlator. You basically have particle 1, particle 2, then you also take a difference between reaction plane. You can also expand it in terms of the cosine and the sine. And the cosine represents the in-plane, the sine represents the outer plane. And you can sort of see, like, it's not hard to see why it works, because in this very ideal case, imagine you have two positive going out and two negatives going down. We take a difference of the angle. In a pure CME scenario, well, this alpha and beta means the sign of charge. So you can have different opposite sign combination and the same sign. Yeah, so they will give a different sign from this correlation. And also, you have to take the difference between the opposite sign and the same sign. This is to cancel out this charge independent backgrounds. Yeah, so the background doesn't depend on charge. You know, you see that in this ideal case, you get something positive, right? And this is indeed what Starr and Alice both have shown a long time ago. Here, what plotted here, okay, x-axis is centrality, y-axis is actually, here it's not the delta gamma, it's just the opposite sign and the same sign. And you can see, if you take the difference, it's indeed positive. But the problem is that they did it for lead and gold. They find it very similar, but they are very two different systems. So the fact that you get something same means you're not really seeing the signal. You're seeing something like a background, because they're not supposed to be the same. And what is a bit more convincing is this small system collisions. So they also collide like P-lead or any other stuff. And you can see that from the small collision, basically, if you collide a proton with a lead, in this case, you're not supposed to have any CME, because the magnetic field direction is random. You not really have a well-defined two spectator creating this magnetic field. And the fact that you see this correlator give the similar value means that this is very heavily dominated by background, and it's something charge-dependent background. And this is what I said before. It's the local charge conservation. It's coupled with the elliptic flow. And just a bit more detail on what is elliptic flow or this tropic flow. Basically, at the initial stage, you have a pressure. It's not the same. And then this is some anisotropy at the beginning. Then you have this expansion, and this will translate to this momentum space anisotropy. And you can sort of imagine it. So what I mean by elliptic flow, the reason I say coupled with elliptic flow, because it's dominant phase. We have something like distribution like this. People do like this expansion, and this elliptic shape is dominant contribution. So this also means if you look at here, you have more particles coming out in the same direction of this reaction plane. And in the case of, for example, okay, you have rho 0 degree to pi plus 1 minus. You basically have more particle coming out from the reaction plane, and this essentially just give you the same thing that you think is the CME. It's similar. Give the same value to the CME. the CME contribution. Okay, so well, also I want to show a bit about how people calculate this, how I calculate this gamma correlator. Well, you look at it, it looks similar. Right? You just put the like cosine and three number, but it's done with this also well-established mathematical cumulant is well used in flow. I want to say a bit about this, but by giving an example, like what is cumulant. So imagine you have two random variable x and x1 and x2. If they are statistically independent, then their joint probability distribution can be factorized. You can write them like that. But if they are dependent, you also have to add another this term, which is talk about the genuine correlation between them. And this is what we mean by this cumulant, basically. In the context of particle physics, we usually just call it like this is a genuine two-particle correlation. It's called also called second order cumulant. And in this case, we are talking about three-particle correlation, and there's also the genuine correlation between them. So if you have three x2 and x3, you can also do it like expanding like this in a very pictorial way. And basically, what we care is this last one. This is a genuine correlation, and written out in a bit more like a mathematical term. We will want to calculate this. Okay, so then that is just like a experimental observable. But this is the reason I introduced that before is that it is used in this method, which I used for my CME analysis. So the method I used spectator-participant, participant plan, and here what we change is that instead of just if you remember before, I just put a reaction plane, but here you can take two kinds of plane. So first it's called the spectator plane, another one is called the participant plane. You have to make two choices of plane, and if you look at on the right, the participant plane are produced by the particle which participate in the collisions. They're like this part. Yeah? And the spectator plane is produced by the spectator. And well, they should be relatively similar, but the difference is that the spectator created the magnetic field directly. So this spectator plane should correlate directly to the CME signal because it's driven by this magnetic field. But the participant plane is a plane that the flow is maximize the flow. The flow is maximized. So also in this method, well, so we calculate delta gamma for two types of plane, and also we divide by the elliptic flow. This is to cancel some. This some just trying to keep details, but I just show it for completeness. This is nice because it cancels out first the flow, the background. The scale you normalize it with your flow background. Also, you cancel out this band plane resolution, so you don't have to deal with the resolution of the plane. Okay, so in the end, we want to take the ratio of these two, and as I said, this spectator plane is coupled strongly maximum with the CME maximized. So if you take the ratio of them, you should see something. If CME really exists, you should see something larger than 1. And this method has also been tried by the Star collaboration in the global creation. They tried they extract something called the fraction of CME in the end. So this like the fraction of CME in this observable, and they do see something like a few sigma significance. Okay, so in Alice, the main difficulty is to get this spectator plane, but because you have to use this 0 degree calorimeter to get it, and we don't have a very good resolution for this. Okay, then I talk about some highlight of analysis. Specifically, one of them is this calibration because it took so much time to work on this. So ZDC in Alice is basically located at the beam rapidity. It has the A and C side. It consists of it's a 2x2 towers. You have tower 1 to 4, which is labeled for each tower. And also have tower 0, which also measure the total energy of them. Okay, so this calibration Was also people also did it before, but there was some problem with it. So this is what I come in and fix it. So I call this standard procedure, which is basically what everyone did before in Alice graduation. So the new approach is what I tried. So you start with its gain calculation. The point is to equalize the each tower. You make sure the gain is properly set. And in old ways, you basically force each tower to have the same average energy. But this is not true because each tower doesn't have to have the same energy because you can have a slightly different gain. So I did a linear fit to provide a better calibration for the gain. As you can see on the right for the old method, if you plot the sum of the 4 tower versus this tower 0, in principle, you should see a 45-degree line. And then all the method is a bit more broad, a bit more spread out compared to this new gain calculation.
Sorry, I guess maybe I misunderstood what you said. I mean, on average, each tower should have the same energy.
Yeah, but it's the hardware, so it doesn't have to.
But I thought you said, so then maybe I thought you said the problem with the calibration procedure in the old method was that they forced them to have.
Yeah, they basically divide this by 4, then they put average in to scale with 1/4 of the power 0. And this.
I see, okay.
Yeah. But because also each is just optic fiber, it's PMT, right? You can have different gain for them. They can have slightly different gain.
Yeah, understood. Okay, thanks.
So I think what you're saying, instead of taking average over all,
Yeah, you take
divided tower by tower.
you basically you sum it, but it was coefficient in the front.
Right, so it's a weighted mean instead of just a mean.
And indeed, you see that it gives a sharper correlation. Then is this shower central position. So this central reconstruction. In all the ways, basically, the idea is you take the ratio of like top and bottom. You get sort of the relative position of the y, and then also take the left and right. You get the relative position of the x with some parameterization. This worked fine for 2010, but somehow in 2018 it became more and more square. So what I used was to make adopt this paper, use this another way, logarithmic weighting. And with this, I think in this method, it takes care of the tower with a very low number, take care of it better with this logarithmic weighting. So you can see that, well, I cannot see this is a huge improvement, but if you look at the contour, it's a bit more square. Another thing is this recentering. Basically, you recenter your average. You basically recenter this spot to make sure the center of your detector aligns with the beam. Basically, that's the idea. And in all the ways, you basically have a very high dimension histogram. You save every position, you subtract it. It's very complicated. And also in 2018, you can see that this is the average spot on the X and Y positions. Actually, during the beam run, it actually changes when you have the leveling on. The leveling actually change the beam hitting on the VDC. And it's very high dimension if you do this, and it really can run out of like the statistics. So what I did was also do a list of square feet, put all these relevant parameters, including this time dependence. And this is a bit hard small to see. And what's shown here is this, the distribution of the spectator-participant. Because the recentering is to make sure it's flat. Just like what you do with DBC, you have this like a phi distribution to be flat, something similar. Well, you can see from the old calibration, it's a variation. It's actually quite big. And in a new method, if you look at just C side, its variation already smaller. And if you combine it, A and C side, and what I mean by combine is basically if you have a C and A, if you on two sides you have two spots hitting like this, combine it, you just draw a straight line and to connect them, you get the angle like that. So when you combine it, you get even less variation. So okay, So now I come to the point of this ratio of the spectator plan and the participant plan. And in 2018, we have in Alice two data set, 18Q and 18R. And we also show this on the y-axis is the ratio, and the x-axis is the centrality dependence. And it's the fit with the strict constant line is shown at the bottom. And the point is to show that compare with this old method of calibration, it's this here I only show the split spiral intentionally. The systematic is done because I just want to show like a comparison of how the systematic split spiral get reduced. So compare with this fit with the old method, it get reduced by quite a bit. But still, in the backup slide, I showed the same plot with the systematic error, but the main systematic error source is the ZDC. So for example, for the 18Q, it's roughly the same size of this error. You check the backup slide. Okay, so then we have to constrain, we have to extract this fraction of CME inside this gamma correlator, the other gamma correlator. And this is by solving for these equations, you get these parameters. And for the 18Q, we get a limit of around 33% at 95%. And 18R, this is also discussed in our floor plan meeting. I think your idea is that we will drop 18R because first it's error-wise bigger. Because this has also been checked quite extensively, because ZDC is performed a bit worse in the 18R. And if you look at the correlation of A and C side, if you plot this angle, this is some pattern that I don't know really what's going on, because ideally you should see the 45-degree line. And also if you combine A and C side, you compare with your participant plan, reconstruct it with V0. You also don't get a very 45-degree. And this is looks much better in 18Q. And also even combine this result with this, it doesn't really make the final conclusion different. So it's decided to drop it. So as a conclusion, well, in Alice, we first got this method complete for CME. And also, the result is compatible with low CME. We have a final limit of 33%. Okay, now I talk a bit more with this AVFD model. So this is a Monte Carlo style.
So I guess before you move on from that one, let's put that in context. How big were you expecting it to be? I mean, I guess there were two statements there: compatible with zero and an upper limit. But
yeah, because if you see something like significant, you will see something like a star, right? You want it to be like something like this, right? If you see something like this way different from the zero, which means you have this would mean like 20% of your delta gamma has a contribution from CME, something like that.
right, but you told us in the earlier slides that you don't expect the same answer from Star or LHC and Rick. So
sure.
So I guess is 33% bigger or smaller than you were expecting it to?
Well, 33 is upper limit, but I think if you're talking about the CME itself, it should be smaller because at high energy, the magnetic field has a shorter lifetime. So it's so you should because the whole this chirality imbalance is driven by the magnetic field. If it's magnetic field decays like within like as I showed 0.5 per C, or before the formation of QGP, probably it's too hard to really separate the charge. Yeah.
Yeah. I was just wondering, like,
there's no like a theory prediction for the number because there are many unknown. Even this transition rate we don't know. So the theory cannot give us a number for like we should say like 5%, but they expect it to be small.
But I guess at the LHC, Alice in particular has made many CME.
Yeah, sure. This is also in the this is in the, I put.
I'm just curious where you are. Like, is it?
So
this one was supposed to be a sensitive one, right?
Yeah. So this is like well the current status. Well, in probably the last generation of measurement, they'll get something like 20 to 30%. And it's only with this Alice eventually engineering, which is this exactly same method, but compared to like this is 2015, I think. And then they run it on 2018. Then they get something like 5% or 6%. But they are different methods, I could say. Also, they have to rely on Monte Carlo simulation. So to predict the magnetic field dependence. And as I said, these two, this my analysis and this analysis will be published together. So yeah. Yeah. Okay, so come back to this AVFD model.
Yeah, so just a basic question, like when you say like 33%, how did you get that number from like the minus 0.096 thing that you mentioned?
Yeah, this is also a point. Like if you talk about especially I think astrophysics, or some neutrino people they care about, because in principle you cannot get negative percentage. It is something physical, right? But for us, I think first you cannot get a prior, so there's no prior experience. So you need like a Monte Carlo maybe like to simulate what's the prior knowledge of this percentage. Yeah, because for sure the probability for the CME signal to be like 5% is bigger than it's being like 90%, because if 90% we would have been seen it. But we don't think we have a reliable prior, so we just take two times this uncertainty.
I mean, like, how do you get the number, or like?
Yeah, so you add this by 2 times of this, because 1 sigma is 60%, the 2 sigma is 95%, or something like this. So it's a bit naive, but also we don't have a theory for the prior.
Okay, so it's like 33% no CME effect, or 33 like?
No, so the CME signal is less than 33% at 95%. So the CME contribution to this delta gamma correlation, the value of this delta gamma correlator is less than 33%.
Okay.
So if this value is like 1, we expect the contribution from CME to be less than 0.3%. Yeah.
Okay.
Yeah.
Maybe one other question before we move on.
Yeah.
So to connect back when you showed the star and Alice result where there was a hint, but there was like a signal, right? So
Well,
do I
it's
now
1, 2, 3 sigma, so I don't think you say anything.
the one before where you said it was all background?
Which one?
I think it was the first or second slide, or
This?
the other one before.
The motivation slide. I
Yeah.
think.
Thank you. I was just trying to connect
This
this
one. This one.
now. So then if I'm taking what you said now at the end where we had to include the background, so now I should read this result as that they didn't have the, how do I connect like your conclusions back to this result? Were they?
So this result was just measurement of the correlator. So you just see the value of the correlator, but the value of correlator doesn't give you the signal, because it's heavy. The point is to show this, the value of the correlator is heavily contaminated by background. You have to take this correlator, use some other method. So this method also uses this correlator, but it measures it with 2 different kind of band. Then take the ratio of these 2 band, you cancel out the background.
Can I think of another way of it being that for this measure that you're showing us here,
Yeah.
at most 33% of it is signal, which means that 66% of it is background.
Yeah, that's
If I take your upper limit as the
Sure,
answer, right? So
sure.
we're measuring background dominantly, I guess.
Exactly.
Okay, yeah.
When we are still on this topic, so you showed this correlation plot, right, with size ZDAs to see, right?
I mean,
These 2 plots which look like an interference pattern.
this one, right?
These ones, yeah. So well, it almost looks like an interference pattern to me, like a Moore pattern or something.
Yeah.
Is there a reason for that? Like,
I don't know. So this is really, I think no one really understands. I also show this
because
to.
if you're looking at correlation, typically if it's linear, you say they're correlated. If it's circle, you say not correlated. But it's an interference pattern. It's kind of
Yeah.
so.
What is the difference between the two samples? So it's like just a difference in like,
Okay, so
They were taking-
this is the difference of the sample is not you cannot explain it for this. I think first you have the correlation is changed, but I don't think it.
so it's something that happened with the detector.
I think no one really understands this.
They're separated in time, like one was like
Separation.
the first half of the run
Like,
and then second
I
half
can
of the
show
run, right? Or
this,
second half of the data taking period.
This is
First
this
half.
is in 18Q. This is like a reason you see this, but still like the background to noise ratio is not very like nice, but this at least is clear that is expected. But this is something just strange.
So in the star measurement, they separated out like the red and blue and different centralities. So and then one is like consistent with no CME or something like that, and then one has like this greater than 0. So why don't you do that in elites?
No, it's just different centrality. What they do is take different centrality. In principle, like this to this kind of centrality ranges should have a bigger signal. Yeah.
Yeah, so like if you separate your data
Oh,
points
okay.
into different centralities, will you see a signal in
Uh,
some?
Yeah, so this comes to the correlation of ZDC. So where did I put it? Maybe at the end. Oh. Okay, so if you look at this is basically showing the correlation of ZDC. You have the x direction correlation, y direction correlation, and xy correlation because like orthogonal. You should not see any correlation like this in xy because they're perpendicular. Basically means if you move in the y direction, you should not see moving in the x direction. Yeah. But what you see that in the ZDC is that if you plot the xy direction, xy correlation, they start to cross 0 and become positive at this point. So this is not something. Oh, sorry. The xy is fine, but okay, sorry. I was with this thing about this x and y direction because this is the in the y x for example in the x axis, right? We are looking at A and C side. The two spectators hit like this. They should move in the opposite direction. If you one go to left, another one should to right. And then you should see something negative correlation. But at some point it crosses 0 become positive. So this is also something physical. Means the detector has some problem at this point. And it's roughly at around the 50% centrality. So in Alice, the detector actually cannot be, you cannot trust it after this. So that's why it's not used.
I see.
Okay, so yeah, finally AVFD model. So this model is similar to basically any kind of a heavy ion simulation. You have to start with this global initial state, then you have this hydro expansion, and after the expansion, you have this Cooper Fryer for this hydronization. Then you have this URQMD for the hadron scattering, scattering. And what is being special? What is special about this model is that first, because this model is dedicated for 3ME. You have this special feature, which is you have in the initial state, you also have this electromagnetic field being simulated. Also, you have you can inject this chirality imbalance in it. They call this N5 or S. S is the entropy. So another special feature is at this hydronization. Basically, it's a hypersurface of this at the end of this hydro extension. You can add this local charge conservation. This is like the background. So basically, this model lets you to have the signal part, also have the background part. Okay, so this for this part, I actually have to come back to this experimental observer before I talk about this gamma correlator. Yeah, I also have to introduce another one called it's two-pattern correlator. So basically, CME, you look at the charge dependence autoplane. So autoplane direct flow. If we expand this, this is the distribution of the Azimuthal distribution of the particle yield. If you look at the autoplane, basically you have to describe it in terms of the sign because the opposite for like up and down. And look at this delta correlator. It's a minus, but here is plus. And the net effect is that if you write in terms of this A, you just have different sign. That's the point. And this different sign in a point make it possible to, this is essential because it make it possible for us to make an unambiguous parameterization to extract the optimum level of the background and the signal. And the point of this study is we try to get the optimum value of this LCC and chirality imbalance. And use it to try to set optimum value to describe this the correlator. And you will see it more clear here because here is a simulation of the lab and the xenon. And you can see that we have this baseline. Basically, you have a zero background and zero signal. And you have here you only switch on the background. Here you only switch on the signal. Yeah. And basically, when you switch on the background, if you increase, you will see that this also move up. Both of them go up in the same direction. But when you have the signal switch on, because I say that you have a different sign in front of this in previous slide, you have different sign here. They move in opposite direction. So this is what make it possible to make an unambiguous distinction. And with this kind of relationship, you can parameterize like this is the background, and this is the signal. You plot it for you plot this dependence for both delta gamma and delta correlator, and you see a quadratic dependence on this signal. It's also because it is quadratic, so you have a quadratic dependence, but it's linear depending on the background. But basically, from this, it's easy to get from this relationship. You can just easily get your optimum background and the signal value. And basically, what plotted here is the value we extracted for the background and the signal, which is able to describe the measurement in the data fairly well. So, yeah, this blue is just blue data point from lattice. You measure it, and this we put in for each centrality being we put in this optimal value, and you can see it describes its measurement very well. And by looking at this part, you can see that for the xenon, if we average over all the centrality, for xenon, you have a expectation of something consistent with zero because two sigma basically is zero. And for the that, you need something actually quite significant deviating from zero to be able to describe the data. But of course, don't confuse this with FCME, like fraction of CME before. So this is the percentage of chirality imbalance you put in the model. It's not the delta gamma correlate. It's not the like 3%. So
go back one then, please.
Yeah.
Sorry to interrupt you again. But then doesn't that tell me that the CME signal is 50% because the background is 50%? Not from your end, but from your LCC. You say
no. This is like this means like well, this is not really like describing the background level inside your delta gamma observable. This just means in the model at the surface of the hypersurface of this hydro extension. Yeah, at this hotspot you have to emit particles from the Cooper file, and then you artificially make sure that here it means 50% of particle emitted from this full cell. You have to have this charge conservation. Have a positive, negative, positive, negative. Yeah. But this just means it's a model parameter. It's not the experimental observable. Yeah, but this means for the system to describe the observation, we need some sizable signal input into this model to describe it.
Can you not now turn that around from your model and tell me what F should be? What to do with that value of N being 0.03? I mean, is that 90% FCM or 2%?
Yeah, sure. You can of course, if you switch off this and you take the ratio, then you will get the amount of if you simulate it with only background, right? Then you take the ratio of the switching on the signal. You can see the percentage between them. Yeah. But these are all very predictable because you can see the relationship, the way they move. This is linear. This is also quadratic. So basically, it's quite predictable. Unlike how much percentage. Of course, you can think. Yes. But we didn't do this final calculation putting either signal or either background. Yeah. Okay. I hope you are still following it. It's quite different from the jet. Please just ask questions. I think if you confused.
So you have confused me because.
Yeah. Okay. So please ask.
You arrived at the conclusion here that there's a significant amount of CME. Isn't that what I deduced from M5 over N3?
It means the chirality imbalance. How many imbalance of the quark you have to put in? This is 3% of the quark you generate at the beginning. You have to have a chirality imbalance.
Which sounds big.
Yeah.
And is the CME signal that I have a chirality imbalance is what the CME is?
Okay.
But then you come around with your measure and said, which represents the same data, because you say you fit beautifully the data, and I agree, the AVFD fits nicely the Alice data when you put those parameters in, which is good. And I guess your data is consistent with that data by the Shi.
Yeah.
And then you deduced that there wasn't any CM.
Yeah, but basically you already can see you need the signal input. Of course, you can also calculate delta gamma or delta and get a fraction of CMU.
I guess, do you get to a self-consistent picture? Because your first analysis said it's consistent with 0 or tiny.
Ah, sure.
And your second analysis says it's big. I feel like 3% chirality imbalance is large.
Sure.
I mean, maybe not. Maybe 3% is still small.
Well, I say this background scenario. So also it's error, but it's very big in the first analysis, right? If it's it just means the signal level is below 33%.
Right, but if you take this, sorry, maybe I'm not phrasing my question well, so I apologize. But if you plug in that, would that say that it's less than 33%? Like, do you get a consistent?
I haven't tried it.
Like, what is the value
Sure,
of the F that you would
you
get
want to say
given these two?
You want to say a direct comparison of one-to-one comparison. It's like
I guess, are they consistent with each other? Like, because if this comes out and says, okay, that means the fraction of the CME is 20%, you've got a nice consistent picture. Otherwise, how do I know that AVFD is doing anything reasonable? Sort of.
Sure. We haven't tried, but I think we haven't tried to get a fraction of CME, but I think you want to see if it's consistent like 33%. If it's go above or below. Right?
Yeah, but if you when you have your delta gamma and you have everything there, right?
Yeah, sure.
And if you come out from this and say, well, to pick the data, I need a FCME of 90%, we're kind of in trouble.
But I think also I want to say that the goal of this study was originally we came up was not to check this other method if it's consistent. The point is to check two different systems. Like it is expected that Xenon doesn't have a smaller signal than that because Xenon also has a smaller system. So that was the original idea.
Mm-hmm.
So it's indeed compatible, like as we expected from
So the right-hand side plot, like the bottom right blue points are what you showed in your first analysis, right? The data that you.
No, this is just Alice measurement. So you have measured this a million times. So this is just you take the data, this delta gamma correlation.
So it's not with the SP method that you.
No. SP method this method they always use this delta gamma correlate. So
But you also measured delta gamma over V2, right?
yeah, okay. So this is a bit more technical if I explain, but okay, if you look at this delta gamma, like this is what I say by measurement. You take a measurement from them, right? You can calculate the delta gamma from this plot. Yeah, this is already being published. You can take it. You try to make the model to match them. Of course, this point should compatible with my my calculation. Of course, it is, but I didn't do comparison here. But also here you cannot do a direct comparison. If I calculate this, you cannot really compare because here I don't divide by this event plane resolution because it's being cancelled out by this V2. It's just a bit more technical. Yeah? So here, because also for Alice, we cannot estimate the event plane resolution for the spectator plane very well. If you calculate V2, if you calculate this part, V2 spectator plane, is something not reasonable, which means that the estimation of the event plane resolution is wrong. Yeah, but it can cancel out in this ratio, so we don't have to get this event plane resolution. Yeah, this is a nice thing about this method.
So the 33% and the N5 over S, like those are from different measurements.
Yeah.
Like even when you compare with data.
Yeah, but here it just you don't divide the event plane resolution. If you divide the event plane resolution, it's the same. If you for the participant plane, if you divide the event plane resolution, it's the same.
So delta Y of the participant plane angle is the same as the original measurement.
Yeah, sure. Yeah, it is the same.
And yeah, okay.
Because here
You just did a trick to cancel the trick is to cancel the resolution.
Yeah. So this
Okay.
here, they always divide the irration plane, which is the participant plane. They always calculate this with the participant plane. So the particle which participate. Yeah. But here we take all the spectators. Okay, so is everything clear or I should no question? Please ask.
So I guess like how like you haven't compared their previous measurement with your AVFD model, but is there anything you can compare your newest measurement with the SPPP method with any theory prediction or like?
There's no theory prediction. So
Okay.
yeah. So in Monte Carlo, we cannot simulate very well the spectator. There's no Monte Carlo which does a spectator simulation. Yeah. There's no realistic simulation. So yes. So
But you should still be able to compare because I thought you take in a model, you know where the spectator plane is.
model
Yeah.
yeah, but they don't really simulate the spectator plane. You can set it to be 0 as your spectator plane, which you think is because this initial state you have this anisotropy case in the spectator.
But could you not find the plane? I mean, it's a model, so you know the truth everywhere that maximizes your signal because you said that's why you want to go to the spectator plane. Right? So
Yeah,
maximize your magnetic field, for instance, because you've got a B field in there.
Yeah, the model indeed put the magnetic field to be always perpendicular. That's true.
That's effectively then your
That's effective.
spectator plane.
But it's not. You don't deal with the fluctuation between the spectator and the participant plane. Correct. I think there's no fluctuation. You just set it to 0. Then you think it's always the.
Right, but then that's, I mean, why, I thought you said why you wanted to go to the spectator plane was to enhance the magnetic field, which enhances the separation.
Yeah.
So 0 would be the spectator plane for what you care about from why you're getting at the spectator.
Yeah. Okay. So I think this model is too clean. model is too clean it doesn't have the fluctuation of the spectator plane. So,
But that's okay, isn't it? Because you try and take that out by actually, instead of saying it's at 0, you're changing the angle because in reality, in the data, you wiggle it. I completely agree, right? And so that changes. But in your model, you don't wiggle it, so you don't have to worry about it.
yeah, but then the prediction, you have to judge if it's if you can really see it, I think. So you want to get a model parameter which give you the same spectator plan, participant plan, like ratio, something like that, right?
Well, I guess like the OGR, couldn't you calculate something to compare to your data? And
Yeah, you can do it in that way. That is sure.
I mean, you could just set that to 0.
Just say there's something to be more careful about, which is the model doesn't deal with this spectator plan realistic. So of course, there are people who, I think people in start, they did try to just take spectator plan to be 0, the participant plan, whatever come out, you reconstruct the participant plan. That is possible.
Right.
Yeah, but yeah, I'm just saying, bit more careful with this. Yeah. Okay, so as I said, in conclusion for this study, the AVFD, yeah, so we try to get the optimal variance to describe the signal and the background to match these two kind of observable in the data for both PP and Zeno collisions. And for Zeno, we see it's a consistent background scenario. And for the flat, we need a sizable input for this direct imbalance to be able to reproduce the data. But of course, this is model dependent. Huh? So you have to trust the model, which is 100% accurate, which is not exactly.
So maybe back again with the xenon. So the xenon also had a value of the.
Yeah, sure.
So why is just because it's smaller? Why is that consistent with the background only scenario?
So you don't have to see a need in a zero. You don't see. Also, I think in this xenon paper, they also try to extract the fractional semi is compatible with 0. So we use this Monte Carlo to check. That was the originally goal for this study. So in the xenon, and also Alice did the xenon for the CME. They used it's another different method to get the fractional CME. It was compatible with 0. And in the model, we do see that you need basically negligible signal input. Yeah. Okay, so this is one slide just talking about this radiation hardness test. And I give an example. This is one of the chip designed at Nikhef, which is it's called a voltage controlled oscillator. You see this chip is output voltage which oscillating with the frequency which you can control with input voltage. Yeah? The point is to test it into the radiational hard. And what I did was learning to use LabVIEW and control all this kind of equipment. And here is just a plot of showing that. So on the x-axis is accumulated radiation. And on the y-axis is frequency output with different input voltage. So this VCO will give you different oscillation frequency with different input. And the deterioration is quite small. But there's a gap because the laptop crashed. It's on Sunday, so we didn't notice for like a few hours.
So this is radiation hardness of what?
Of the chip.
Of which chip?
Well, you put on the X-ray. So they also put it in a nuclear cancer. This is like two kind of radiation.
So no, I meant chip for ZTC or like.
No, this is a VCO. So it's like just checking it. Like I think the point is to tuning the time. Like,
so this is just a component.
It's a component. Yes.
Okay, so
it's a small chip. It's not for ZDC. And they also have other chips. Like they call this a band gap. So you also test those.
Then how did you do the radiation? Like where did you get? How did you radiate it?
Certainly, this is X-ray machine.
This is just a X-ray photon, X photon. Okay, I see.
They also put in the nuclear plant for like 3 months.
Right. So you are only concerned about the gamma photon radiation.
So as I say, they also put in a nuclear plant, so they have a different kind of radiation. So like a neutron, right?
How do you know how much radiation you accumulated? How
Yeah,
do
okay,
you-
so the some people know this, they tell us, so you can set, machine, you can set the strength of the radiation. So you accumulate it with the time, so this is a megawatt, so some
No, I
units.
mean, you need to sort of monitor somehow, right, of how much radiation you're exposing.
Yeah, there's no monitoring, there's no like sensor like, detecting like how much you're
Yeah.
accumulating,
So
but
it just,
we set a value. And it should be conservative enough to like, and we put it for quite a long time, a few days, I think, under this X-ray machine, like,
And then you're setting it to a constant voltage and seeing that. the
it's, so this is, the value you take care of, it actually do a scan of the voltage. Right, it just like tick, and scan, and also take a measurement of the, its frequency with the oscilloscope automatically. So just record the data. We don't have to be there and change it with hand.
I guess I want to make an oscillating voltage to. Why does my chip want an oscillating?
I think it's for timing. So you just better you have to know the timing of the. I think it's for the timing. Yeah, but okay, it's a bit quite hard. I
yeah, I
remember
mean,
it was
even
fun.
for rate, right, to
synchronizing, I think.
you always put like an oscillator circuit on your front end electronic. Right?
Is it for synchronizing then?
Yeah, for the, yeah,
So you have a pulse.
right.
Oh, yes.
It's the timing. And these oscillators are kind of, when dark radiation hard, so there's a whole thing about them, like how do you pick them? But you don't have results for like neutron radiation test or
I think they just got it back.
I see. Because they are the worst one, X-rays are fine. Do you know what was the energy of these X-rays?
I forgot. I forgot the number. Yeah. It's quite a while ago. This I did like 2 years ago. So, I think in the end they will publish a paper on this because there was a bit delay on the publication because the company which help with the technology doesn't want it to be public. So it's because the radiation like happening. So it's a bit
Oh, sorry, this is silly, but you said this is a gap on Sunday, right? So it seems like your time axis is like a week or two. That's performance, right?
the timing is a few days. I think 3 days.
3 days.
It's from like Friday to Monday. So.
Okay, but is it actually good to only deteriorate 3.5% in a few days if we're putting this in some?
No, the strength of the radiation is much much stronger than
I
we
see.
get in the detector.
Okay.
So I think the ALICE has some requirement to be like it's much less than this, so it's okay.
Okay.
So the hardware design team they have to meet some number we set. This is fine.
And it's mega red, it's
Yeah,
huge.
right. Okay.
Okay, so a bit more future research interests. I hope I'm not too naive about some ideas because but currently I'm not the expert in jet, and I think I was reading quite a bit in the last few months, and some measurement came across me, which I find was interesting. The first is this measure of this low X gluon distribution for PDF. We do like a digest or heavy vector measure measurement. This photo production process in the UPCs. And this allows you to probe the gluon distribution at a very low X. And it's important. You also can study this nuclear shadowing, which means if you take the ratio of the nuclear gluon PDF versus proton gluon PDF scale with this 8 atomic number, you can see that the shadowing means there's a suppressing here. So this it's less gluon seen in the nucleus. And also you can look for this gluon saturation effect. This is so this highlighting the long range fan sink as well. This is quite an important question, even for the one of the main design purpose for EIC. Yeah, and I see this because also I saw people talk about when you do this measurement that you can have this ambiguity. Basically, you can have either high energy, because when you have this photon scattering of gluons, you can have either low energy photons scattering with high energy gluons, and this is dominant, 95%. And then also you have high energy photons scattering with low X gluon, but this is what we want to measure. We measure very low X gluons, but it's only 5%. And both contribute to this cross section. And there's some ambiguity, which is, I see you can use DDC to measure the energy with different cases. You have zero neutron on different sides. You have a neutron on one side or neutron on both sides. And this allows you to disentangle it. Because I work quite a lot on DDC, I thought this part I know a bit. But also I need some knowledge of getting this digest and heavy frame meson, heavy vector mesons. And also in round 3, we should have a very high acceptance. Another thing is, okay, so this, I saw it, first I saw this photon tag or boson tag jet, which allow you to get the energy of this jet, you have a good understanding of the energy of the jet. But then I also saw a talk by Hobart. He talked about this eventship engineering. And in his talk, I saw that you can have some, if you correlate with event plane, and this fast bands difference was significant with this enough. And then I came to realize this was also work done by people here. Yeah, I thought this also would be something nice. Of course, I think this gamma effect and zeta ejector is because of the acceptance of values. So it's, the statistics will drop. But also in round 3, you have a lot of statistics. So I don't know, maybe jet people can really say if it's feasible. Another thing is just my of my personal interest, because the CME measurement is super hard. And it's also, I think it's frustrating for everyone that they didn't find it in the end. And I think the strategy at this point, I think it's good to going back to measure this initial magnetic field, which has never been measured. People have tried. This is what is the observable called delta B1. It's a directed flow of the we measure it for the mesons. And you can see for the point is to see the slope of it. We take the difference of D0 and D bar 0, and the star actually and Alice have a bit confusing direction. And also the model. If people have tried to fit a model with different, you can see here this different, for example, the lifetime of the magnetic field. You try to predict the slope. I think you need a bit better measurement to really give the theory people of the model. Yeah. So yes, I think that's it. That's all I want to say. Thank you.
Thank you very much for the nice talk. Do we have any additional questions? Also on Zoom.
I have a quick question.
Yeah.
Maybe I was running around taking pictures at the time or something, but can you go back to around slide 62 or 61? Yeah. Maybe one or two more back. Basically, I was wondering when you make actually, yeah, if you go ahead, I'm sorry, to 62 again. When you make the comparison to the release data, this is a true prediction. You get the values for N5 and LCC from the model, and then you apply that to the.
You apply the simulator again, because here we don't only took a few data points, which is quite far away from each other.
Yeah.
Yeah, but yeah, we even put like a 10% of signal in. But you have to extract at which point you land for the data. That's the point.
maybe, so you said that you also were comparing this event shape engineering method. And the percentage was smaller, is that what you
it's
said?
much smaller.
Yeah,
actually.
so but then you said it's model dependent,
Yeah, because
so I guess is that model dependence included in the?
yeah, so you see, like for different member models, the Glover and the Tranquil, they're both similar to similar field dependence. Then well, it's slightly different, but okay, at least you have to use a model to extract the limit. And for this method, the method I use is canceling out, so you don't need any model to as input. Yeah, and especially this model of this magnetic field have never measured, so it's very hard to even they find the signal here. It's hard to convince people the model is 100% is a discovery. So you need something more work here to convince people. Maybe you have to measure a magnetic field at least.
So I'm just curious, you've mentioned three or maybe like several future projects. Which one would you think you would start with first, or which one are you most excited about?
I think the first and the second was well, I think this is my personal interest, so I don't have to do it. But I think these two, well, I think this is well more. This is like much more established measurement. People have done this measurement. So nice to continue in round 3, for sure. And I find it quite interesting. This is, I think you need to think a bit more. I'm not sure because I was told the statistics can be a bit more problem. So I don't know how many events we really have because you have to use event shaping engineering. It's a bit more differential. You also have to correlate with the event plan. You also have to make a selection of event shape because you also reduce your statistics. So I don't know in the end if you have enough event to see how it. Yeah.
Yes. So this is Tom speaking from Zoom. So since you're on here already, can I ask a further question? Yeah, so I'm wondering like what physics you're after by, studying like the Z boson using event shape engineering. Like, are you trying to look at say the V2, or are you looking at to see, for example, I mean, there shouldn't be any, quenching effect or whatever with Z bosons, right? So I'm just like a little bit slow on, what message you're after and what you should be expecting with this study here. Or like what observable do you think you will measure? Yeah, thank you.
Yeah, observable. I have to think a bit more. Not from jet side, but naively, I think if you know the original energy of the jet. If you know the path length, is something interesting. Yeah, if you ask me what kind of correlation, I'm not sure.
Okay, thanks.
Something like measure AJ or XJ as the others who call it versus in plane, out of plane or something.
Sure. I mean, naively, you correlate just with the plane angle, you measure its energy. Yeah, but you take the ratio of in plane out of plane. This is just like a very naive observable. I'm not sure if it's a better, more robust observable for this. Maybe I can check Katie's. Does she have some observable there?
I mean, she just looks at the jet with respect to the event plane, which I think.
Yeah. Okay.
Because the way I'm thinking about it, like if you do exactly what Katie did for jet by accepting Z, then when you look at Z's interaction with the QGP, which is none, then yeah, I I'm like thinking, what effect you're you should see. But yeah, okay, this is like still future interested, so we can definitely muse about it, later in time. Yeah, all right, thank you.
I don't know if I think he's just saying using the Z to basically tag the energy scale of the jet and then just looking at like jet event shape engineering. It seems like you're thinking that he's using the Z to see if there's some effect on the Z of the medium, but I don't think that's the case.
Oh, okay. So we're
The
actually
Z-tag.
the Z-tag jet.
Yeah.
Ah, okay. Yeah, sorry. Now.
So it's yeah, it's a Z-tag jet because it is supposed to be a clean tag. Yeah.
Okay. Sorry, my fault.
Of course, the Z is transparent for the leptons. When it gets to lepton, it's transparent to the QGP.
So given Z's are so rare, so this is a sort of more generic question than just to you, right? So now we real-time track, or will be real-time tracking any day now. Could we filter Z's offline by finding, I was thinking about your comment about we need high momentum electrons, and okay, the calorimetry is small, but the TPC, could we just tag events that have two very high momentum tracks? Yeah, because that would get me to a Z somehow, right? Can't do EDX online, I wouldn't have thought, but even calculate the invariant mass or have them boosted close together or something so that okay, Z's are rare, but we find them all.
I think you have to check the efficiency of TDC for the PP efficiency of the TDC.
But I mean, our efficiency is good at high. Our momentum resolution is terrible, like we were talking, maybe, but it only has to be roughly in the right mass range, right? Just to take those ones, there won't be many. Have two high momentum tracks with a small opening angle, because I guess there's boost. I don't know. I just wonder if there's a way one can now we track, use the TPC as a trigger somewhat more.
Yeah.
Is there a muon detector in at least?
Yeah.
Can you detect Z2 mu plus mu minus? What's that? I don't know.
What's the coverage? I know that on two sides.
It's forward, right?
It's forward.
Oh,
So
okay.
It's not the cover.
Okay.
There. Yes, not fully covered. No. Okay.
I don't think so, no.
So it's
I know
just-
these are
Yes, I'm
definitely a trick. Yeah, I don't know. Yeah, these are.
I mean, they're hard once you've taken the data, right? Because there's just not many. We don't have much calorimeter coverage, but I don't know whether one could do something smart now you have tracks in the TPC.
Yeah.
I say it doesn't have to be wonderful momentum resolution also. Take the highest two and see is the moment invariant mass somewhere in the right range.
Yeah, I think, yeah.
We're taking all min bias, we've got to have Z sample, same Z sample as CMS.
Right. I mean, they're taking in all, so
Right.
they should get as many as they can,
There is.
as there is, they should be able to get, so then you could filter it out. Yeah.